Hello, future engineers. This is part 4 on 2D frames. Still, the principle is free body diagrams and also finding two force bodies if there are. Level 16, the top of the folding workbench has a mass of 50 kilograms with mass center at G. Calculate the X and Y components of the force supported by the pin at E. So this is pin at E. So we put the weight 50 times 9.81 newtons. Then, because there are no other inclined loads, the horizontal component at A will be 0. We'll call the vertical component as AY. Then C is a roller, therefore this is R sub C only. So considering the entire system, moment at C is 0. Clockwise positive, so you have AY times 1200 minus 50 times 9.81 times 750. Then from here, we can now compute AY. It is equal to 306.56 newtons. Then if we draw free body diagram of the upper folding workbench, this one, the reaction at B will be the same as reaction at C. The vertical reaction at D also is the same. So therefore, RB equals RC equals 50 times 9.21 minus AY, which is 306.56. So R sub B equals R sub C equals 183.94 newtons. Then we draw free body diagram on member AEB. So we have here the tension, distance from the top 225, so distance from E is also 225 because the total distance, vertical distance is 900 and this is the center. So therefore, half of 900 for 50. So 450 minus 225, so that's also 225. Anyway, that's not needed. Then we put the reactions at A and at B. So we can solve now the tension if we set moment at E0. We can also solve EY if we set RY equals 0. So let's begin with RY equals 0. So we have equals 306.56 minus EY minus 183.94. So from here we can solve E sub Y, which is 122.6 newtons. Then that's the answer. Then to solve for EX, summation versus extension equals EX. So let's set moment is 0. So take note EX equals T. So moment is 0, counterclockwise positive, so that is equal to T times 225. Then minus 306.56 times 600. Then minus 183.94 times 600. So solving for T, which is equal to EX, equals 1308 newtons. Therefore, the X and Y components of the force supported by pin at E is EX 1308 newtons and EY is 122.6 newtons. So that's it for this problem. Next, neglecting the weight of the frame, find the tension in cable CD. So here is the given figure. We will call the reactions here as EX, E horizontal and E vertical. Then at D, F horizontal and F vertical. So let's just assume the direction shown. So this is our plan. We sum up moment about E. Then we have two unknowns FH and FD considering the entire system. Then after that, we draw the free body diagram of AB since it is entirely loaded and bounded with pins. We conclude that the vertical reactions at A and B equal and it is half the load. Knowing the vertical reactions at B, we set summation forces Y to solve for FV. Then from the first equation that we established, we can solve now FH. Having known FH, then this is the tension. We set moment B0. Let's draw the free body diagram of this part, then we can now compute the tension. So that's the flow of the solution. So moment E0, considering the entire system, counterclockwise positive, so that is equal to FH times 1.8. This is 1.8 because the given figure is just this. So 5.4 minus 3.6 is 1.8. Then plus FV times 5.4 plus 3.6 is 9. Then minus 3 times 5.4. Then moment arm 2.7 or 5.4 over 2. So establishing the first equation, 1.8 FH plus 9 FV equals 43.74 kilonewtons. Call that equation 1. Next, if we isolate member AB, which I will not, I just explained, A vertical equals B vertical, and it is equal to half of 3 times 5.4. So 3 times 5.4 over 2. Or you set moment A0, take moment about A equate to 0, then you will get the same results. So A sub V equals B sub V equals 8.1 kilonewtons. Then substitute here in equation 1. So to do that, we apply, because it is upward here, when upward at AV is also upward because the loading is downward. Then when we transmit it to this member here, the upward force will now be downward 8.1. And let us say BH is to the right. And this is the tension. So we can now solve FV, which is obviously 8.1 kilonewtons also. This distance is equal to 2.7 as in the figure. So FV equals 8.1 by summing up forces vertical from this free body diagram. Then we substitute the value of FV in equation 1 to solve for FH. So 1.8 FH plus 9 times 8.1 equals 43.74. So FH is equal to negative 16.2 kilonewtons. So meaning to say I wrongly position or direct the FH, but it doesn't matter. Next, we set moment B0 clockwise positive, so tension times 2.7. Then plus FH times 3.6. Take note, carry the sign because FH is not change direction. Then minus FV times 3.6. So substituting values where FH is negative 16.2 and FV is 8.1 here. So 0 equals 2.7 plus negative 16.2 times 3.6 minus FV 8.1 times 3.6. Then we can now compute the tension. It is equal to 32.4 kilonewtons. The walkway ABC of the footbridge is stiffened by adding the cable ADC and a short post of length L. If the tension in the cable is not to exceed 2 to 50 newtons, what is the smallest value of L for which the 850 Newton person can be supported? For L to be smallest, then the person must position himself at the center of the beam. Or else, if he positions anywhere on this beam here, on this horizontal platform, then L will not be the shortest one. So he should position himself at B, so that the reaction here is equal to, vertical reaction is equal to half of 850. This is 425. The tension is limited not to exceed 2 to 50. So therefore at C, RC vertical equals 0. the force on the beam is not included, and secondly, there's no force because this will just slip. So RC vertical equals 0, so 425 minus the vertical component of 2250. The vertical component of 2250 is 2250 times sine of this angle. Sine of this angle is L divided by length of CD, which is square root of 2.4 square plus L square. So equals 425 minus 2250 sine of this angle. Sine of the angle is opposite L over hypotenuse, which is the length of CD, square root of 2.4 square plus L square. So 425 over 2250 is 7 over 90. And what is left in the right side is L over square root of 2.4 square plus L square. Square both sides, then cross multiply. So 289 times L square plus 2.4 square. I just, by commutative law of addition, you can do that. Then 90 square is 8100 L square. 289 times 2.4 square is 8100 minus 289. L square is 7811 L square. From here, you can solve for L. The shortest value of L is 0.4616 meter. The weight W equals 9 kilonewtons hangs from the cable which passes over the pulley at F. Neglecting weights of the bars and the pulley, determine the magnitude of the pin reaction at B and D. So pin reaction at B and D magnitude. So we will call the horizontal component of reaction at A 0 because there's no inclined load considering the entire system. And the vertical reaction AV at E, because this is roller support, R sub E. So that is 0. Summation forces horizontal considering the entire system. So that's 0. So let's solve for AV then RE. So moment is 0, clockwise positive. So we have AV times 4 minus W, which is 9. The moment arm is 0.4 plus 2, 2.4. 9 times 2.4. So A vertical is equal to 5.4 kilonewtons. Then RE is 9 minus 5.4, or R vertical component of resultant equals 0 considering the whole system. Then it is equal to AV plus RE minus W, which is 9. So RE therefore is 3.6 kilonewtons. Then we draw the FBD of the horizontal member BFD. So by principle, we remove the pulley and put at F, the center of pulley, the tension 9 kilonewtons downward and 9 kilonewtons to the right. So if we look at the figure, because 9 is at the center, then vis-a-vis equals vis-a-vis equals half of 9. Or you sum up moment about D, vis-a-vis times 2 minus 9 times 1 equals 0. So vis-a-vis is 4.5. So vis-a-vis is also 4.5. So vis-a-vis equals vis-a-vis equals 4.5 kilonewtons. That's the shortest way because the horizontal load is along the axis and the weight W 9 kilonewtons is at the center. So having found vis-a-vis and vis-a-vis, it is only the BH and DH that are to be computed. So let's draw the left portion of this frame. Action, reaction, remember? Then you just assume these directions for C. So since we already know vis-a-vis, which is 4.5 here upward, so here it's downward. Then if we set moment at C0, we can now solve for BH. So moment C0, counterclockwise positive, BH times 1.5 plus 4.5 times 1. By the way, this is 1 and 1, or 2, half of 2. because B is the center of ABC. That's why you just divide 2 by 1. 2 by 2. So 1 meter by 1 meter. Then minus 5.4 times 2. So from here we can solve BH, 4.2 kilonewtons. Then the magnitude of the pin reaction at B, square root of BH square plus B sub V square, or square root of 4.2 square plus 4.5 square. So from here, R sub B can now be computed. It is equal to 6.155 kilonewtons. This pin reaction is also called shear force in the pin. At D also, we call that shear force in particular. Then, for RH equals 0 for this horizontal member, so equals negative BH, which is negative of BH 4.2, then plus 9, then minus DH. So DH therefore is 9 minus 4.2. It is equal to 4.8 kilonewtons. Then we only have D sub V left. So to solve for D sub V, we draw the free body diagram of the right part. And we have tension, by the way, at this part. The radius is 0.4. So that's why this is 9 kilonewtons, the weight, tension in this cable. And because the radius is 0.4, the distance of 9 kilonewtons from C, the moment arm, is 1.5 minus 0.4. That's why we have 1.1 here. So D sub V is 4.5 and DH is 4.8. So therefore, we can now compute the magnitude of the pin reaction at D, square root of 4.8 square plus 4.5 square. So R sub D is equal to 6.580 kilonewtons. So let's check this free body diagram if MC is really 0. If it is 0, then all these answers are correct. So considering clockwise positive, so 9 times 1.1 plus 4.5 times 1, that's clockwise. Then minus DH times DH is 4.8 times 1.5. Remember, this is 1.5. And minus 3.6 times 2. So using your calculator there, MC is 0 exactly. So that means all these answers are correct. So level 20, the frame structure shown supports a load W equals 4.5 kilonewtons. Assuming ideal pins at all joints, find the compressive force FBC in the bar BC and the shear force RD. So that's why we call this pin reaction as shear force on the pin at D. So that's the specific term. The pulley at E has a radius of 0.3 meter. Actually, this is just a simple problem, but based on my experience, my students were not yet able to solve this. So that's why I consider this as level 20, but not as intense as levels 21 to 25 for the last part of frames. So let's transmit first the tension force at E. That's the free body diagram. Then finally, this member here, the free body diagram of CDE. By the way, member BC is a two-force body. So FBC is along the axis of BC. So we replace that in this free body diagram here. Then the angle that FBC makes with the horizontal, this angle here, is arctan of 0.9, because that's 0.9 divided by 1.2. And that is 36.87 degrees. Then at D, let's just have horizontal and vertical components. Let's just assume rightward and upward. Then if we set moment at D0, we can solve for FBC. Then RH 0, we can solve for DH. R vertical 0, we can solve for DV. So as simple as that. But the trick is many students were not able to draw this FBD. You may tend to solve for reaction at B, which is bad. So MD is 0. There are two components of FBC, horizontal, which is counterclockwise, and vertical, which passes through D. So let's consider counterclockwise positive. So horizontal component is FBC cosine of 36.87, and it is compression because it is pointing towards the point of application. Then the moment arm is 0.9, then minus this 4.5 here times 0.9. Cancel 0.9. So FBC is 4.5 over cosine 36.87, and that is 5.625 kilonewtons. So it is a compressive force as shown in the figure. Then R horizontal equals 0, and it is equal to DH minus 5.625 cosine of 36.87, and minus 4.5. So solving for DH, d sub H is 9 kilonewtons, and its direction is correct in the free body diagram. Then R vertical equals 0, then it is equal to d sub V plus 5.625 sine of 36.87, and minus 4.5. So d sub V can now be computed. It is equal to 1.125 kilonewtons. Finally, the shear force at D is square root of dH square plus d sub V square. So square root of 9 square plus 1.125 square. So R sub D, or the shear force on the pin at D, is 9.070 kilonewtons. So that's it. I hope you were able to follow the solution. You may say that these batch of problems are simpler than the preceding problems, but the tricks in analyzing the frames in this batch made the problem a little bit complicated or tricky.